let's welcome Dr. Koushik Sarkar from University of North Bengal. So he will speak on topological warm-up of partial metric spaces.
Okay, good evening everyone. I am Koushik Sarkar and I am going to present my talk entitled Topological Warm-up of Partial Metric Spaces. So first begin with an example which leads my interest to study partial metric space. Let x equal to s omega be the set of all sequences over a non-empty set S and consider a mapping G from x cross x to x by dxy is equal to 2 to the power minus k, where k is the largest non-negative integer or infinity such that xi yi is equal to yi for each I less than k. Then it is not hard to check that xt forms a metric space. In computer science, every sequence is approximated by a section of it, however long it may be, because it is not possible by writing a computer program to compute a sequence and print out its value in finite amount of time. Now, suppose our definition, or consider D, if we extend it to Y, the set of all finite sequence over S, then D fails to form a metric only for the reason dxx equals to 2 to the power minus k. That is for non-zero self-distance. So the natural question arises: is there any generalization of metric space axioms so that we can introduce the non-zero self-distances, and so that the familiar metric and its topological properties such as Cantor intersection theorem, Baire category theorem retained? Partial metric space appears as an affirmative answer to this question. S.G. Matthews introduced this, and in last 3 decades, many mathematicians, Alcuin, Baggio, Tourmaj, Oltra, Valero, have studied partial metric space to some extent. In this article, we have considered a suitable definition of convergence of a sequence in a partial metric space. We have introduced star closed sets in partial metric space and study the relationship among star closed sets in partial metric spaces and its induced metric spaces. Also, we have shown that Cantor intersection theorem and Baire category theorem can be achieved in partial metric space. And just preliminaries. So Matthews defined a mapping P from x cross x to R plus, where x is a non-empty set, is said to be a partial metric if it satisfies the following conditions. This one is the equality implies indistancy and symmetricity, self-distance property, and this is the modified triangular inequality. And then the XP is said to be partial metric space. And Matthews defined the convergence of a sequence in XP in such a way that xn is converges to x if limit n tends to infinity pxn x will be pxx, and a sequence xn is a Cauchy sequence if limit n tends to infinity pxn xn exists, and if partial metric space xp is complete if the Cauchy sequence in x is convergent in such a way that limit n tends to infinity pxn x equals to pxx is equal to limit n tends to pxn xn. Okay. Now we consider an example. First, we once again, this is the definition for convergence according to Matthews: limit n tends to infinity pxn x equal to px. Now we consider an example, and we are taking x equal to r plus and pxy is equal to maximum of xy. Then it is easy to check that this forms a partial metric. Now we consider this sequence xn, this 1 2 1 2 1 2, this type of sequence. Then this sequence also convergent in x, which is absurd. So we consider the definition of convergence of a sequence in a partial metric space as in Baggio. Baggio, Cooperman, and Buckton they have done a paper in 2009 in American Mathematical Monthly, and they have considered this type of this definition of convergence, where they have extended this portion limit n tends to infinity pxn x pxx equals to limit n tends to infinity pxn xn, And accordingly, as the definition of convergence changes, we consider the definition of a complete partial metric space as if in this space every Cauchy-sequence is convergent therein, and there is no change in the definition of Cauchy-sequence. In partial metric space, if we define the functions dp and d omega in such a way, d omega xy to pxy minus pxx minus py, where p is a partial metric, then we can see that d omega is a d omega forms a metric, and the same results hold for dpxy, where we can define dpxy as pxy minus minimum of pxx and pyy. Then this forms a metric. We called it induced metric, induced by the partial metric p. In 2012, Altun and Durmach proved this following result, which will be very useful in proving so many results in partial metric space. They proved that the convergence of a sequence in a partial metric space is equivalent to the convergence of a sequence in its induced metric space. Throughout this paper, we by a closure P we mean the closure of A in XP, and by simple A closure we mean the closure of A in its induced metric space. Now we define star closure. Once again, we consider an example. Let A equals to open interval 0 to 1, and the same partial metric on R plus P, where P is equal to maximum of xy, then a closure P is 0 to infinity. And if we take A, any point A from A closure P, then we cannot get any sequence xn in A such that xn converges to A. Xn converges to A in the sense of Dajou's definition. So sequence lemma does not hold. So we now define star closure in such a way a star closure equals to A union L, where L is the limit of a convergent sequence in A, and A set A is said to be star closed sets if A equals to a star closure. Here is some similarities with star closure with metric spaces. We can see this also holds for metric space. And partial metric space generates a T0 topology. It's not even T1. There is a doubt about the uniqueness of the limit of a convergent sequence therein. We remove this doubt by proving the following result. This is the proof. Just using the modified triangular uniquity, we can show that the limit of sequence is unique. Now, so this is also similar to metric space, that is star closure is a closed set, and here is the proof. I will not go through the proof because time is very short. Okay, now here is some relationship between the closed walls. Any closed wall in XP is a star closed set in XP, and here is the proof. Just using the definition of star closure, we can prove this. But the converse of this theorem is not true. If we take R plus with P, where P is a function, P maximum of xy, and A is 1, 2, 3, 4 singleton, then A closure P is not equals to A, but A star closure is equals to A. So A star closed set may not be closed set in a partial metric space. Here is another theorem. It states that any star closed sets in XP is closed sets in XDP, and we can prove this theorem using this equivalency of convergence in XP and XDP, and this is the technique of this proof. And this is another example which shows that if a closed set in XDP may not be closed in XP. Now this is a theorem which states that if xn converges to x and yn converges to y, then limit n tends to infinity pxn yn is equal to pxy. Now we will prove Cantor intersection theorem. Before that, this lemma will be very useful. So this lemma tells that in a partial metric space xp, if xn is a Cauchy sequence in xp, then it will be Cauchy sequence in xdp and vice versa. And if xp is complete, then also xdp also be complete. And both this condition is equivalent. So proof A part A is done by Altun, and we prove the part B, that is if XP is complete, then XDP is complete, and if XDP is complete, then XP is complete. Okay, and this is the sketch of the proof. Okay, now we define diameter of a set in a partial metric space. So we define diameter of a set in a partial metric space in such a way that P of A equals to supremum of Pxy minus Pxx for all xy in A. And like in metric space, we can show that diameter of A is equal to diameter of a star closure. And this is the proof. Finally, we are proving Cantor intersection theorem, which tells that a partial metric space xp is complete if and only for every sequence fn of star closed sets satisfying fn plus 1, that is nested sequence of star closed sets, and its diameter tends to 0 as n tends to infinity, then its infinite intersection is singleton. And here is the proof. This sketch of the proof is that just we take a Cauchy sequence, and using this we will consider this fn xn plus p minus 1, and we will show that this fn plus 1 is star closure satisfies this condition a and b, that is nested and its diameter tends to 0, and then its infinite intersection contains a non-empty, and so it contains an element x, and using this we can show that this is the proof. Now, Bayer category theorem. First, begin with some definitions. A set B in a partial metric space xp is said to be nowhere dense in xp if every open set U in xp contains an open set V, so that V intersection V is equal to phi. And a partial metric space is said to be second category if it cannot be written as a countable union of nowhere dense sets. Otherwise, it is a first category. Before proving this Bayer category theorem, we will prove this lemma, which will be very useful. It tells that a closed ball in a partial metric space is not a is a star closed set. A closed ball in a metric space is a closed set, but here is closed ball may not be closed sets. This is an example that a closed ball may fail to be closed set in partial metric space. If we take R plus P, the same P, then we can see that BP01, which is a closed wall, is not a closed set, and this closed wall is actually star closed set. And this is the proof that a closed wall is a star closed set. And here is the final theorem, which tells that every complete partial metric space is of second category. And we prove this, but this theorem actually can be proved without using Cantor intersection theorem. Here we prove this using Cantor intersection theorem only. So we proceed this theorem by contradiction method. We just take x can be written as a infinite union of no hair dense sets, and just using this no hair condition, dense condition, we have created a sequence of closed star closed sets, and then using Cantor intersection theorem for in partial metric space, we can show that XP is of second category. And these are the references I used to prepare this paper. and thank you all.
Thanks, Koushik.
Okay, thank you.
If there are any questions. So you have a partial metric space, right?
Okay,
Space with a
okay.
partial metric.
Okay.
So how you generate the topology? Like how
Okay,
you
okay,
how
okay,
your
okay,
open
okay.
balls look like?
Okay. Its
Right.
open balls
Or,
look like pxy y in x such that pxy less than pxx plus epsilon. Here is here is the difference because like metric space dxx is 0. Here for partial metric space dxx may not be 0. So we define here open balls pxy less than pxx plus epsilon.
okay. If there are any more questions. Okay. Okay. Thank you, Koushik, for a nice talk.